Good evening. Welcome. Thank you for coming to the 2015 J. Tuzo Wilson Lecture, sponsored by the Physics Department. I didn't know J. Tuzo Wilson, but as a young student taking 8th grade earth science in New York State, I was drawn to the beauty of the mechanism of plate tectonics, which is what J. Tuzo Wilson is famous for. I'm sure some of you in the audience do know him, and I'm sure that you could regale us with tales of his exploits. But the thing that's always struck me, as I said, is the beauty of this underlying paradigm that unifies all of Earth science, and that's what J. Tuzo Wilson has left us. The same spirit of exploration is very much in evidence in the drive to understand the fundamental physical processes that drive the other planets in the solar system in the work of my colleague and our speaker, Professor David Paige. Dave is a professor of planetary science in the Department of Earth, Planetary, and Space Sciences at UCLA. He got his BS at UCLA in geophysics and space physics in 1979. He went on to get a PhD at Caltech in planetary science in 1985. Dave has been involved in planetary missions, mostly through NASA, for the last 40 years, ever since he was an undergraduate. He's been the principal investigator of the Mars Polar Lander, my favorite instrument, the Diviner Thermal Radiometer, which is operating on the Lunar Reconnaissance Orbiter, currently in orbit around the Moon. And he's the deputy PI for the RIMFAX GPR instrument that's about to go to Mars on the Mars 2020 rover. Dave is the recipient of NASA's highest award, the Exceptional Scientific Achievement Medal, for his breakthrough discoveries on the thermal stability of volatiles on the Moon and Mercury in 2013. Without further ado, let's welcome Dave.
Thanks, Rebecca. And thanks to all of you for coming to this lecture. When I mentioned I was coming out to Toronto to give a talk at this distinguished forum, one of my colleagues said, what's next for you, Dave? Lifetime Achievement Medal or something like that? And I said, oh gosh, yes, well, we'll see. But, you know, putting a talk like this together that covers the entire solar system is actually a really good therapy because it helps put the field into some perspective as to sort of as well as my role in it. And in my own analysis, I would classify myself basically as a prospector for ice in the solar system, a professional in some respect. And what I'll do in my talk is give you sort of a tour through the solar system and show what we know about solar system ices and their overall significance in terms of how the solar system works and its habitability. Before we get started, we need to define the topic. So we all know that matter has typically 3 states: solids, liquids, and gases. And when a volatile substance is in a solid state, we call it an ice. And here we have some Japanese snow monkeys enjoying all 3 states of matter simultaneously, as you can see here. So what is a volatile? Well, I went to the Wikipedia and typed in volatile, and it provided this very informative definition. It's an adjective, substance that's easily evaporated at normal temperatures. It's also liable to change rapidly and unpredictably, especially for the worse. The origin of the word volatile comes from volare, which is to fly. And those of us that study volatiles, or even just observe them in day-to-day life, are often amazed at how they're able to move around and fly around and appear and disappear. They really are quite magical and have many of the same qualities as in the sci-fi movies that Alien Blood has, except, of course, we all know them as our favorite volatiles. In terms of other preliminaries, we should also define what some of the main volatiles are that we'll care about in terms of these ices. So here's a list of important solar system ices in this column. their chemical formulas, and then their vacuum stability or thermal stability temperatures. These are defined as a temperature that a volatile would be at in either degrees Kelvin or degrees Celsius, if you're more comfortable with that, that if you put them out in the solid form in a vacuum and just let them sublimate, which is go directly from their solid to their vapor forms, what temperature they would have to be at to sublimate at a rate of approximately 1 meter in a billion years. And they're in order of increasing volatility. So the least volatile ice is also the most abundant ice, which is water ice, the familiar water ice which we use and drink almost every day, or at least try to drink. We can chew it, I guess. It's great stuff. It has a volatility temperature of about 110 Kelvin. A surface that's below that temperature, you can probably keep ice stable over a significant fraction of the age of the solar system. Other more volatile ice includes ammonia ice, NH3, pictured here, carbon dioxide ice, slightly less, more volatile, pictured here, methane ice, which is very volatile, and in fact it's flammable in our environment on Earth with oxygen, and then the most volatile ice that we'll be dealing with, which is nitrogen, which has a stability temperature of 16 Kelvin. That's only 16 degrees Celsius above absolute zero. Now, it's interesting when you look at the compositions of these ice, there's actually quite a variety of molecules. In fact, if we sort of add them up, we'll notice we have carbon, hydrogen, oxygen, and nitrogen. These are the famous CHON molecules, which are essentially the building blocks of organic molecules. And these are, of course, what make life itself possible. They also make organic molecules like ethanol, which we may have after the seminar today, possible as well. But the idea here is that in addition to being interesting in their own right, they provide raw material that can be ultimately recombined and turned into the organic building blocks for the origin as well as for the continuation and sustenance of life in the solar system. And so that's another theme to the talk. Another preliminary is a discussion of solar system temperatures. And this is one of the few graphs I'm going to show during the talk, but it's a plot of a very simple-minded calculation of what the average global temperatures of a planetary body should be along this axis here. So it's a log scale, 10, 100, 1,000. And then it's distance from the sun in astronomical units, where the distance between Earth and the sun is defined to be 1 astronomical unit. This is the type of calculation that an astronomer would do after discovering a new planetary system and try to do a rough calculation of what temperature a newly discovered planet might be. And you can see, of course, there's a strong decrease as we go out from Mercury past Uranus and Neptune and into the Kuiper Belt. And it's traditional to also define a so-called habitable zone, which is roughly defined by the range of temperatures over liquid water would be stable. And in our solar system, the Earth is smack dab in the middle of the habitable zone, and Venus and Mars are at the edges. There's also another important line, which is called the water ice line here. This is the distance from the sun where you might expect to start to find bodies whose surface is covered with thermally stable water ice. And this line in our solar system occurs roughly around 3 or 4 astronomical units in the middle of the asteroid belt. And so objects beyond the asteroid belt and Jupiter could be expected to have surfaces that are covered with water ice. And this is an important prediction of this type of model. It also has big implications for the formation of the solar system, which and early evolution of the solar system we won't get into in this talk. So let's start our solar system tour and considering our planet here, first planet from the sun, Mercury, which according to this should have an average temperature of something like 400 Kelvin, which is very, very hot. Here's a Mariner 10 picture of Mercury. Mercury is, often defined as a parched, lifeless world that's basically a cinder orbiting the sun. It has a cratered surface, no atmosphere, and it's a ridiculously hot place that one could never imagine providing much in the way of habitability. I remember in the early 90s being in a Mars meeting, and one of my Mars colleagues, who was a radar astronomer, took me off from the corner and said, "Dave, I got to show you something. Look at this. This is the first images we've taken, the radar images of the planet Mercury. And look at this thing up there. It's got like a polar cap." And he also showed me this. Later on, we got data in the southern region, and it also showed that there was a radar image that seemed to show a polar cap. A lot of times when you bounce radar off of objects, you get strong reflections, and this reflection we saw in the North Pole of Mercury was a dead ringer for water ice. So I thought about this for a little while, and I said, Marty, I know exactly what's going on here. There are places near the poles of Mercury, which actually has no tilt to its spin axis. There are places, even though it's so close to the sun, where there's craters in there, and the walls of the crater are able to shield the sun from ever shining on the crater. This is literally a place where the sun never shines. And because of that, it does not ever get hot, and it's super cold in there, and these craters are filled up with ice. So we did some modeling. We showed that, in fact, even though Mercury is the closest planet to the sun, there are places right at the poles that never get any sunlight, and it's super cold there, and it's cold enough to have ice. Later, we got beautiful high-resolution images of the north and south polar regions of Mercury, and the bright deposits turned out to be localized in very specific impact craters that were surrounding the North Pole. Interestingly, these were craters that hadn't yet ever been imaged in visible light. No spacecraft had ever seen them yet. The radar for Arecibo was so good it could actually see the craters and the ice there. So the only significant question was, well, what kind of ice is it? Is it actually water ice? And the answer to this came after the Messenger mission to Mercury, which has just recently completed this year after crashing in, got a beautiful topographic map of the polar region. And with this map, we were able to use rather sophisticated thermal models to calculate in detail what the temperatures were inside these craters here. And basically, it's a perfect match. All the places that we see ice in the radar are very, very cold places. The temperatures are down around 100 Kelvin or lower. And so this beautiful correspondence between where one would predict ice to be based on thermal considerations, where we actually have evidence from Messenger, is a wonderful result. Another thing Messenger did was to actually take some images of this crater here, Prokofiev. It has a very large water ice deposit based on the radar and the thermal models. And there's enough scattered light inside the crater that the imaging system could do a long exposure and actually peer into the darkness in the crater, just in the same way I can sort of see you out in the audience, even though you're not directly illuminated. And what came out was just amazing, because here's the ice deposit. You can see this very clear boundary here, which corresponds exactly to where it should be thermally stable. This sort of provides the seeing is believing sense of closure you get when you're doing science. And this was a very gratifying image from all of those us that were involved in the whole endeavor. So let's go back to our solar system water lines again and see where this astronomer's model stacks up. Well, it turns out when you really look at Mercury, of course, it doesn't just have a global average temperature. There are all sorts of cold niches inside Mercury, or around Mercury at various latitudes, that would bring its range of average temperatures to look something more like this. This, of course, means that, as we've shown, that Mercury is actually both outside and inside the waterline. And of course, when we look at other planets, we'll find out there's a lot of diversity there as well. A good case in point is Venus. Venus, as we know, has a thick atmosphere, hundreds of bars of pressure, and an extreme greenhouse effect that makes it the hottest average temperature body in the solar system. It's completely off the line. I think I'm just going to throw out this diagram for the rest of the talk, because it's not that useful when it comes to our solar system, it turns out. The next step on our tour is going to be the Earth, but to be more precisely, the Earth-Moon system. Here is a really cool sequence of images that were taken by NASA's Deep Space Climate Observatory. This is a observatory that stays between the Earth and the Sun and takes continuous images of the Earth, and it shows the Moon, of course, orbiting in front of the Earth. Now, just thinking back to the diagram again, the Earth and the Moon are exactly the same distance from the Sun to first order. And to first order, you might think, well, they ought to have similar climates, but you couldn't find a more different type of place, the Earth versus the Moon. The Earth, of course, is our wonderful home water planet, covered with clouds and all sorts of great stuff, whereas the Moon is much more like Mercury. It's a cold, lifeless, airless body with a very boring geologic history in general. And you can see it's much darker and whatever. I know Rebecca's cringing here because we all like to work on the Moon. But you got to admit, compared to the Earth, the Moon is pretty dull. And so let's first talk about the Earth a little bit, and then we'll talk about the Moon, and specifically about ice. So the big story about ice on Earth, of course, is that it's declining. Most of the water on Earth, 97%, is the form of liquid water, and less than 3% is in the form of the ice. But the 3% of ice that we have is observed to very clearly being on the decline. Here's some runoff from the Greenland ice cap. The history of ice on Earth is a very complicated one. We know that during the last million years, we've been in a period of fluctuations in which, wow, a picture has left from my, something over here and it doesn't exist now. Anyway, at any rate, there's been fluctuations in the climate that led to very large-scale variations in the cover of ice that we have. For instance, as recently as 20,000 years ago, the entire continent of North America was covered by kilometer-thick ice sheet. The very place that we're sitting right now was covered by kilometers of ice, and that's all been cleared out by now. And these fluctuations have been recorded as variations in temperatures in ice cores, as well as variations in carbon dioxide concentration from the atmosphere that we can see in ice cores. And this extreme sensitivity that we see in terms of the ice volume on the Earth is fundamentally due to its volatility. Essentially, we have a volatile situation going on in the Earth. And this has, of course, been exacerbated because during all this time, we've had humans in various forms whose basic modus operandi is to go around and burn things, right? We started out burning wood, right? And then when we figured out we could start burning fossil fuels or coal, and specifically, things really took off. And the CO2 emissions have basically gone through the roof. You can't even keep up with it anymore. This is a 2008 graph. I like it just because of the way it shows it here, but it's gone up past 400 now in terms of the carbon dioxide concentration of the atmosphere. And then depending on how much of the fossil fuels we end up utilizing or burning in a relatively shorter time, will burn through what took millions of years for the Earth to create by taking sunlight, turning into plants, and then turning into fossil fuels. We're going to go through in a matter of a couple centuries. And what I had here was a picture of another example of humans controlling fire, which is basically the space shuttle taking off. So it's something that we definitely do. If you've ever seen a rocket take off, you're most impressed by the flame and the fact that we can control that flame so well to propel this rocket up. It's a very inspiring thing to see and hear. But at any rate, the impact of humans on ice is very clear. I wanted to show another interesting thing, which was a NASA simulation of carbon dioxide emissions. What's shown here is a high-resolution movie. Whoa, I have to turn it off. A high-resolution movie that shows exactly where on Earth the carbon dioxide is being emitted, as indicated by the yellow and red things. And you can see where our industrial centers are emitting the CO2 and as it's circulating around the globe as it changes the function of season. This is very, very interesting, but really highlights the vast importance of human activities on the concentration of this important greenhouse gas. Another thing in terms of the loss of ice has to do with what's going on in the Antarctic, especially in the West Antarctic ice sheet and ice shelf. There's an East Antarctic ice sheet here, which is on stable land, whereas most of the West Antarctic ice sheet is sort of grounded in terms of a chain of islands. But also, its presence here is buttressing all the other ice in Antarctica. And as this ice melts, you end up in a situation where the rest of the ice in Antarctica can very rapidly go away. And we've seen this. We have great evidence for this when we look at our climate records, for instance, at the end of the last ice age. It only took a couple thousand years for all that ice to go away very, very quickly. Here's a movie that shows the breakup of the Larsen B ice shelf, which is up here. This was recorded by a NASA satellite. And in a period of just a couple months, an area the size of Rhode Island was basically lost from the ice shelf, moved out to lower latitudes, and eventually melted. What makes the loss of ice on Earth of even greater concern is that the measurements we have suggest that it's accelerating, meaning that it's going faster and faster as time goes along. This is indeed a volatile situation, and our ability to predict exactly what the effects of this will be on climate ultimately and our own existence is very uncertain at this point. Turning my attention to the moon, as Rebecca said in the introduction, we have an instrument that's orbiting the moon right now in the Lunar Reconnaissance Orbiter called the Diviner Lunar Radiometer. Here's a picture of it. What it does is it scans the moon and makes global maps over the course of a month. And then over a series of months, we get a full picture of the daily and seasonal behavior of temperatures on the moon. With the data from this instrument, we have more complete information about what the temperature of the moon is than any other body in the solar system, including the Earth. One of the big discoveries that Diviner made earlier on in the mission was that the polar regions of the moon are extremely cold. Here's an infrared image that was taken by Diviner soon after we got into orbit that shows a bunch of craters some of these places never receive illumination and had never actually been seen before. So they were, in a sense, new discoveries. And you can see the temperatures that we're seeing here in degrees Kelvin are extremely low. There are some places on the moon that never get above 30 Kelvin, which is the same temperature that we know, for instance, the surface of Pluto is at. So even in our own backyard, we have some super cryogenic outer solar system environments. One of the main goals of the LRO and LCROSS missions was to, of course, search for the presence of water ice at the poles of the moon. The LCROSS spacecraft was basically targeted to crash into someplace here and then make measurements of the ejecta from the crash to search for water and other volatiles. And we went through a process where we tried to figure out where of all these places to send it. The place that we advocated was right here in Cabeus Crater, where there's one of the coldest places on the moon, and it also was a good place to observe from the Earth. And I suggested to them, look, go for the coldest place, that'll be your best chance to find the ice. The exact spot is shown right here on one of our maps. LCROSS came in and crashed into it. We could actually, from Diviner, and here's a series of images in our various channels, before and after impact, we could actually see the thermal signature from space. We looked at it just as the LCROSS spacecraft impacted, which was very interesting that you could actually see that in our data. What came out of the LCROSS experiment was interesting. Here's our calculations of a histogram of temperatures in the south polar region of the moon, going from 0 to 200 Kelvin. These are subsurface temperatures. You can see there's some very cold stuff and some stuff that's fairly warm. All this area is in permanent shadow, never receives direct sunlight. The place that LCROSS was targeted to was one of the very, very coldest places of the moon, shown here. And then this is a plot that shows the expected thermal stability of a range of potential volatile materials, including water. And basically, we predicted that LCROSS, if it had the capability, would see all these different constituents potentially in the form of ices at the lunar poles. The results of LCROSS were indeed very similar to predictions. The ones that are circled in green are species that LCROSS detected. And these include a wide range of molecules, CO2, SO2, NH3, organics, as well as volatiles, water in particular. Something like 20% water was observed at the LCROSS site, and as well as other things such as mercury, sodium, and sulfur, which are even less volatile than water. So LCROSS represents a tremendous milestone in our understanding of volatiles on the moon, because it provides as close as we have to proof positive that they're present, at least at this one test site. Diviners map the temperatures of the moon in greater detail, and what we've found is that there are places, a large number of places on the moon, where you might expect to find surface water ice, which are shown as white here, and then near surface water ice within the first top meter of the moon in a much greater areas surrounding it. Whether all of these possible niches on the moon are filled with ice and other volatiles is still not clear from the data that we have. The model that fits our data best is if you go deep enough, you can find ice on the moon, but there might be other processes, including micrometeorite impact and processes like that have maybe churned up and reduced the abundance of water ice in the very nearest surface. But we certainly know from LCROSS that right here at least, there appears to be tons of water ice. Why is water ice on the moon important? Well, first of all, sampling it could potentially in the future give us an idea of some of the original volatile material from which the oceans and polar caps of the Earth were formed, as well as maybe a sampling of some of the original organic material that came to originally resulting in the origin of life on Earth. Of course, on Earth, geology and atmospheric processes have erased all of our early records of what happened on Earth, whereas the moon, because of its great boringness, is a historical storehouse of information. You can go to the moon and routinely pick up things that date from the earliest history of the solar system, and because of that, it's very valuable scientifically to us as a preserver of this, and especially in these cold regions. Another reason why it's important is because of the potential for lunar ice as a resource. Eventually, humans will be working and living in so-called cislunar space. The moon, as our closest neighbor in space, is an obvious place to go colonize. And once people are in that area, of course, the use of resources from the moon will be very important. And there are very few things that one could imagine finding there that would be more valuable than water. Water, of course, can be used to drink. You can make ice cubes, as I showed earlier, but you can also break it apart. The hydrogen oxygen, when separated using solar energy, for instance, is the best possible rocket fuel, and that could be used to fuel exploration of the rest of the solar system and beyond. This is a artist conception showing astronauts in the process of setting up a lunar mining operation and extracting the ice for use by lunar settlers. There's another dimension to the ice of the moon question, which is it's going to be very valuable. If you compare how much it will cost to take the water from the Earth, that'll be a rough estimation of a way to evaluate how much ice directly from the moon might be worth to the people that are already there once that economy gets going. And it's been said by many that the first trillionaire on Earth will be a lunar miner. But as someone who's been involved in, sort of in the exploration and discovery of these resources, it brings to mind some interesting questions. When we look at the utilization of resources on Earth, I think it was Buckminster Fuller who described it as a legally piggly process in which basically most of the Earth's resources have turned out to enrich only a very small fraction of the populace. And in many cases, our resources on Earth are used in a market system that basically does not take into account the long-term value of preserving some of these resources for future generations. And we can only hope, and this is, of course, something that everyone would be involved in this type of decision, that resources in space would be used much more appropriately than they've been used on the Earth, and hopefully for the benefit of all of us. Turning next to Mars, here's a Hubble Space Telescope picture of Mars. And when you look at Mars, the word that comes to everyone's mind is tantalizing. Mars seems like it's got all kinds of great stuff going on. It's got an atmosphere, it's got dust storms, it's got water ice clouds, it's got markings on the surface that seem to change. It's got volcanoes and canyons, and it also has polar caps. And these polar caps have been known from telescopic observations to be extremely dynamic in their behavior. Here's some spacecraft shots that show the north and south seasonal polar caps, which are observed to advance and retreat every season with the Martian seasons. The seminal piece of work in my particular field was done in 1966, where Robert Layton and Bruce Murray of Caltech published this paper, Behavior of Carbon Dioxide and Other Volatiles on Mars. And in this paper, they basically argued that the dynamic nature of these seasonal polar caps at Mars could not be explained by the advance and retreat of water ice or snow as we see them on the Earth, Basically, it's too cold. Water isn't volatile enough to give us the sort of variations that we see. And they instead proposed, using data that was newly downlinked to Earth by Mariner 4 spacecraft on the composition of the Martian atmosphere, that instead the polar caps of Mars were composed dominantly of carbon dioxide ice. And this was later proven by many subsequent spacecraft observations. They also included in their work a discussion of exactly how water should behave on Mars. And basically, they said there's some transport from pole to pole seasonally, but most of the water ice on Mars should be below the surface in the form of ground ice. This is a phenomenon we're very familiar with at high Arctic latitudes. It's on the Earth. You dig down through a active layer of soil and then find permafrost in the frozen subsurface. On Mars, they calculated where this frost point temperature should be based on the water vapor content in the atmosphere, and also predicted the boundaries of these frost deposits, and found that basically most areas poleward of 60 degrees north and south on Mars should have abundant ground ice present. In 1992, I published a paper that looked at this in some greater detail and noted that the boundaries that you get for this ground ice actually are extremely sensitive to what you assume in these models, particularly about what the atmospheric water vapor pressure is. And depending on what you assume, or if you have different soil properties, you can get ice that extends all the way down to 30 degrees latitude, or in some cases, that could cover the planet underneath the surface. I don't know if you ever saw that movie, Total Recall, with Arnold Schwarzenegger, where the eyes come bugging out at the end, right? And, one of his big discoveries that there's like ice all underneath the planet Mars. And amazingly, this seems to be a prediction that seems to be coming true. Everywhere we look on Mars, there's lots of abundant evidence for ice. At high latitudes, we see patterned ground and cracks in the Martian surface on a grand scale that suggests the presence of multiple cycles of freezing and rethawing. We also have evidence of hydrogen detection from orbit that shows vast regions in the northern and southern hemisphere at the appropriate latitudes that appear to be contain a significant amount of ice-saturated soil below the surface. There are many glacial features that are observed at a variety of latitudes on Mars, suggesting this ice not only was present at least at some time, but also flowed. And then there was the Phoenix lander in 2008, which landed right here at a high latitude region, and then scooped off the top layer of soil, and then found evidence of abundant ice. So lots of ice in the near surface of Mars. When we look at the Martian climate, we recognize that some of the same sensitivities we see in the Earth's climate to slight variations, for instance, in the Earth's spin axis, or other parameters, again, because of the volatility of the ices, should produce large-scale climate change on Mars. If any planet ought to have unstable climate, it's going to be Mars. And we also have evidence of that, we think, in the form of climate records that appear to be analogous to those that we have on the Earth. Here's a radar scan of the north polar cap of Mars that shows abundant evidence of layering. These layers were laid down during climate epochs that we are currently ignorant of, over timescales we're currently ignorant of, but suggests that if you could drill down and dig down through these layers, you would be able to pull out a record of Mars climate variations. Here's a close-up of one of these scarps here, taken by the MRO HiRISE instrument that's orbiting Mars right now, showing abundant fine-scale layers all the way down to the resolution. These polar layer deposit layers, again, should be an amazing treasure trove of information of Mars once we're able to fully extract them. In terms of deep ice on Mars, we're getting additional data from the spacecraft that are currently working at Mars right now. One very interesting form of this information comes from present-day impacts. These are impacts that are actually forming as we're observing Mars. So the orbiter comes back, looks at a place it looked at maybe 2 years ago, and finds that there's a new crater that was formed. There are many of these all around the planet, and at some latitudes, including latitudes where we wouldn't necessarily predict that ice would be thermally stable today, we find surrounding the crater all this white stuff. This white stuff appears when the craters are fresh and then gradually fades over a period of time, suggesting very strongly that the crater is basically penetrated into an ice table and exhumed fresh ice. So the impact cratering process of Mars is providing us with a window into what's below the surface at deeper depths than we can easily sense. There's also places where there are terrace craters, suggesting that there may be a deep ice table. But these isolated suggestions of ice deposits, which we don't yet know exactly where they all are on the planet, probably a remnant of some previous climate epoch, pale in comparison with the possibility that Mars once had an ocean. And the main piece of evidence of this is just an examination of the Martian topography. This is a view from the North Pole of the topography of the northern hemisphere of Mars. Basically, Mars is divided into a southern hemisphere, which contains highlands of old cratered terrain, more lunar-like, and then a much younger, lower elevation and much smoother northern plains area that has this sort of outline here. When the first topographic data came back, the investigators suggested that these northern plains were among the least rough areas that had been yet measured in the solar system and resembled the abyssal plains of the Earth's oceans in terms of their smoothness. Some scientists initially rushed to the conclusion, this must be a place where there's an ocean. In fact, people were able to map what appear to be paleo shorelines along this boundary here as well, again, suggesting there was an ocean. But scientists are a conservative lot and don't like to just jump in and suggest things such as that willy-nilly. But we've gotten a recent new piece of evidence from the Mars Express spacecraft, which is radar observations that can measure the dielectric constant of the near-surface material. And for this radar, near-surface means to depths of 100 or 200 meters. And what the dielectric constant basically tracks the density. Places that are of high density have high dielectric constant, shown around here, and places that have low density have low dielectric constant. And this is a contour map, a map that sort of shows the region of low dielectric constant and then mapped with the measurements of paleo shorelines that were determined from morphological evidence. And it seems like a very good match. The question is how can all this area be low density? And a potential explanation for this is simply that the low density comes from the presence of abundant ice below the surface. And so this whole northern polar region of Mars could in fact be a frozen ocean, and all you would need to do would be to drill down in it and bring up water that was once in a liquid state, and who knows what might be in it. I'm not saying that this is as profound as Wilson's suggestion of plate tectonics, but it seems like one of those similar situations where you have a lot of different types of evidence, pointing to a particular direction, and it's just a matter of assembling it into a case that it may in fact exist. So Mars could have had an ocean at one time, and the biological potential of that is, of course, very exciting. Let's move out in the solar system some more. These are some beautiful images that were taken by the Rosetta spacecraft this year and the year before of a comet. This is a comet that originates in the Kuiper Belt and makes its way into an orbit that comes close to that of Earth. The Rosetta spacecraft, of course, has stayed in the vicinity of this comet for a long time, and as it approached the sun, it became active, and you can see it spewing out dust and ice here. These measurements are very exciting because it really shows how complicated things can be as soon as you move away from the standard planetary sized and scale of objects. There are, of course, many such objects that basically transfer volatile material in the form of ices from the outer solar system to the inner solar system. And when objects like this hit the Earth, they have the potential of adding to, or in some cases, of subtracting volatile material. The same thing for the inner planets. And it's believed that comets and asteroids that are perturbed into orbits that impact these bodies are a very important source of the volatile material that we see there. What's so interesting is this volatile material has sort of managed to then find a home in the inner solar system and then give rise to basically the very thin skin of volatile material that we see on the Earth. As we move even further out in the solar system, we get to Jupiter and Saturn. These bodies are surrounded by a set of moons, all of which have their own interesting properties, but many of them are now, since they're past the ice line, able to sustain water ice directly on their surface. This is true for Callisto, Ganymede, and Europa, which are major planetary-sized bodies. And then all of these satellites of Saturn are also covered with ice. The thickness of this ice shell on the surface varies. The interiors are rocky, and then you have ice surrounding them. And then in some cases where there's heating going on inside the bodies, you can have a situation where there's a subsurface liquid water ocean underneath the ice shell. This is, of course, something that is very, very exciting to biologists. And one of the most spectacular recent finds by the Cassini spacecraft has been the moon Enceladus. This is a relatively small moon. You can see it has a very interesting surface. And when you look at the limb of Enceladus, you find these geysers or plumes of water-rich material, basically in the form of ice, that's shooting out. When you work back where this had to come from, it basically has to come from a reservoir of liquid water below the surface. And now we have a variety of different ways of inferring the fact that the inside of this body actually is composed of liquid water, which is very exciting. One mystery about a lot of these small bodies that we find in the outer solar system is why they're so active. We don't really understand what the heat sources are, and we don't understand why we're seeing this activity in the present time. They ought to have cooled off long ago. Maybe the volatility of water is an important part of this. No tour as we go out to the outer solar system we complete without a picture of the rings of Saturn. This is taken by the Cassini spacecraft from an extremely interesting perspective. We're basically in the shadow of Saturn, directly behind in a straight line between the center of Saturn and the sun. And what you're looking here are basically the rings with sunlight streaming through them. The rings of Saturn, not surprisingly, are composed primarily of water ice. They're small particles, probably between 10 centimeters and 1 centimeter and a meter in diameter, that ring the planet and are certainly amongst the solar system's most beautiful sights. As we move further out in the solar system, the more icy the bodies appear to be. We mentioned the Kuiper Belt earlier. The Kuiper Belt is a collection of icy objects that exist beyond the orbit of Neptune. We have two large examples that have been dynamically trapped into orbits that bring them close to the inner solar system. One of these objects is Triton. Triton is a moon of Neptune. It's a large, icy body, and it's in a retrograde orbit, meaning it's going counterclockwise, clockwise around Triton if you look down from the North Pole, around Neptune, look down from the North Pole, where most objects are going in the opposite direction. And then our latest star Kuiper Belt object, Pluto. Pluto is in an unusual, eccentric, and inclined orbit. It's a little smaller than Triton, but both bodies have similar characteristics. They are geologically fairly young in their appearance. They also are dominated, at least in terms of their volatile cycles, by not so much water anymore, because at these low temperatures, water has basically become non-volatile and turned into a rock. But nitrogen and methane are the most important volatiles on these particular planets. They've been both observed on the surfaces in the form of ice on these bodies. And as we probably know from looking at the news, the New Horizons spacecraft has flown by Pluto. This is a recent color image of Pluto, and seen some spectacular things. Here's some close-up pictures from New Horizons showing a variety of terrains. There's these interesting bumps. There's these flat regions with these sort of pancake-like structures and these other variegations, impact craters, other things going on here. Everybody in the field is basically scratching their heads when they see these pictures, and it's very difficult to figure out what to make of it, except for a basic statement that there have been a very large variety of different geologic processes that have occurred on this body over time, and we're still trying to sort it out. Pluto also has a large moon that's approximately half its diameter called Charon, and here's a picture from New Horizons of Charon. This is even wilder, where there appears to be a hemisphere that appears to be old and heavily cratered, not unlike the moon, and then another hemisphere that appears to have a lot of other interesting stuff going on it. Again, just like Enceladus, it's mysterious why these bodies appear to have so much activity going on them. In the case of Pluto, one potential explanation comes from looking at Pluto's atmosphere. I have a former student, Candace Hansen, who has been working very consistently on looking at nitrogen cycles on Pluto. The idea here is that, in analogy to Mars, which has carbon dioxide seasonal polar caps, one could predict that based on the temperature of Pluto, that nitrogen would sort of act like that type of volatile and produce seasonal polar caps. And these seasonal polar caps are very interesting because they're so large in their size that they actually affect the total mass of the atmosphere. This occurs on Mars to sort of a 20% degree. On Pluto, the variations in atmospheric mass that we predict are extreme, sort of on the order of 4 orders of magnitude. And so what we have been doing is looking at telescopic observations for Pluto for many years that measure its brightness, and then to the extent that we can determine it, the pressure in the atmosphere, and then use the information we have about Pluto's orbit with a model very similar to that of the original model of Leighton and Murray, with guesstimates as to what the properties of Pluto's nitrogen polar caps are, to predict how it's going to behave as a function of time. So what you see here is a graph that shows some of our results of our best fitting model from the year 1000 to 2000. You've got to be very patient if you work on Pluto, at any rate. And this shows some other parameters, like the fact that Pluto's distance from the sun varies radically because it has an eccentric orbit. It also shows the subsolar latitude Pluto's spin axis is inclined 60 degrees from the normal, so it has very, very extreme seasons. At any rate, our model predicts these huge variations in the pressure of Pluto, sort of on the time scale of its orbit, but as also modulated by its seasons. And a key prediction is that the atmospheric mass of Pluto would increase from basically zero near the turn of the century to a maximum of something like 1/10,000th of the Earth's atmospheric pressure right at the turn of the millennium, and then execute a very precipitous drop, basically as the south polar cap of Pluto, which we inferred to actually be fairly dark, begins to grow during its winter season. We're very excited to find that much of what we predicted turns out to be more or less correct. Here's a picture that was taken by New Horizons that is directly in the shadow of Pluto, and you can see surrounding it is a beautiful thin atmosphere that shows that it hasn't quite completely gone away. And here are some measurements that show how Pluto's pressure has been observed to vary by telescopic observers, and then the latest New Horizon results, which are still being analyzed, show that its pressure is basically going away very, very quickly. So we're excited about that. As we go even further out in the solar system, we find even more ice. Here are some scale drawings that sort of show how the solar system works as you go further on. This is, of course, the inner solar system showing Mars and the Earth in the orbit of Jupiter. And then beyond Neptune is this group of small icy objects which consist of the Kuiper Belt, which surround it. And then at a very much larger scale, the solar system is surrounded by a spherical, to first order, cloud of comets called the Oort cloud. These are the origin of the long period comets, which we basically see unpredictably coming from nowhere, from very, very large orbits, coming right back to the sun and then coming back. This cloud of comets numbers in the many billions and has a mass of many Earth masses. When you add it all up, it's conceivable that there's actually more ice in the solar system in total than there is rocky material, which is very interesting. And here's an example of one of these Oort cloud comets coming in towards the sun and then releasing volatiles. So this concludes our tour of the solar system. I just wanted to summarize with a few takeaway points, and they are as follows. The first is that from all we can determine, our solar system is full of ice. And every place where we're likely to find it, and we've looked for it, we've ended up finding it. This is good for someone like myself, a professional ice finder, in that I'm in a business that is basically an easy one. All you have to do is find a cold place, and you're very likely to find ice in our solar system. Somehow it's figured out, the volatiles have figured out a way to find all these niches and basically fill them up to the extent that they possibly can with ice. These ices also play important roles in terms of shaping the evolution of planetary environments. But because of their volatility and feedback effects, we don't fully understand all the interactions of the ways that they can affect things, and we don't really understand them yet. And then finally, eventually, these ices are going to represent very valuable but finite resources that could enable human exploration of the planet, of the solar system beyond, and it is our duty to use these in a very wise manner once we have the capabilities to do that. Thank you very much. So I guess it makes sense to entertain some questions. I think there are some roving microphones that will be distributed.
Thanks, sir. You didn't. I was waiting for you to specify what you personally found most surprising in the recent discoveries at Pluto and Charon, and perhaps what scientists in general may have found, though I guess you can't answer that question.
Well,
and also, of course,
yes.
with respect to Maki and Eris, the other dwarf planets, what do you expect to find there? More of the same, more, I guess?
As someone who's been in this field for a long time, we're used to flying by a planet and being, completely mystified as to what is going on at first blush. And so the general strategy here is to sort of sit back a little bit and, use your thinking cap and ultimately come to conclusions. So at this point, I'm not surprised by anything that might come back. And that's the beauty of these fields, right? Is that, we routinely are surprised to a very large degree. That's what sort of keeps the field fresh. And the fact we're able to keep going out into the solar system and seeing what's out there of course, makes it fun. So personally, I'm not surprised by any of this. I expected to be, mystified, and we are. Any other questions? There's someone in the back there, I see.
There's another microphone coming around.
Oh, there's another microphone over there. Okay. Oh, it will be here soon.
It's
Okay.
along. Any on this side?
That blue thing, that was just another ring. In other words, there's dust and little particles that are sitting out there, often in connection with moons that are orbiting there that are emitting material and supplying that. So I don't know for a fact what that blue stuff was, but it's more than likely some sort of ring that's being actively produced by some sort of satellite.
Can you comment on where the ice comes from in the first place in terms of the primordial protostar?
Oh, where the ice comes from in the first place. Well, all of these molecules that I'm talking about here are quite cosmically abundant. Hydrogen being the very most abundant, atom in the universe, and then oxygen being, extremely common as well. So it makes sense that out in interstellar space that these, materials will run into each other, and the inevitable union and chemical reactions will occur because they're basically, favored kinetically. So this is all material that was originally part of, the cloud of dust and gas that the solar system formed out of, but did not collapse to form the sun, mostly because of the need to preserve the angular momentum of the original cloud that wouldn't work if you put it all into the sun. So it's the same material that formed the planets. It's just ice instead of rock. Yes?
With places on Venus and Mercury with those craters with such varying temperatures, why don't we find more niches in which there's liquid water?
Well, liquid water is a real problem on Mercury. And that's because, there's a phase diagram for water, and there's a triple point, and that turns out to be at a pressure of approximately 6 millibars. You can't have stable liquid water unless you have a certain water pressure in the form of gas above it to keep the molecules liquid. As soon as you take away that overpressure, only ice and vapor are stable. And so while we have temperatures below the surface on Mercury that are very much in the habitable zone, maybe everything from 80 degrees towards the pole in areas that get sunlight are at some point below the surface room temperature. There's no way to contain the gaseous molecules to create a localized atmosphere to produce liquid water because of that problem. So we don't have liquid water on Mercury, even though that, of course, would be way cool. Yes?
Do you think that there's ice and water in other depths?
Oh, absolutely. In fact, we have pretty good evidence that that's the case. All the processes that formed our solar system are probably not that unique, and in different combinations, we have ice and rock everywhere around the solar system. When I was, going to school and doing my PhD, this notion that there were, planets around other stars was just notional. We had no real, proof that that was in fact the case. And, in the time that we've been doing this, we now know of thousands of planets, literally, compared to just the few that we have around our own sun. So, yes, all the things I've talked about hold equally for other planetary systems. Yes?
You mentioned that the pressure of Pluto's atmosphere is decreasing.
Yes.
How do we measure that?
Oh, what you can do is when Pluto comes in front of a star, you can watch how the starlight gradually fades away as Pluto goes in front of it. And the people that do this are extremely intrepid because Pluto's diameter, is something like, the distance, like the size of the state of Texas or something like that. And you have to go to the exact place on Earth where the occultation of the star is going to take place. So they, get on an airplane, they put get their telescopes out and try to get enough of them so they can see, the star occult different places on the disk of Pluto, and that's how they make these measurements. So yeah, it's quite an interesting process by which they do this. But you don't get constant opportunities. Only when Pluto happens to come between the Earth and a star can you do this. Here's another question.
There are recent reports. There are recent reports of discovery of flowing brines on Mars. Do you expect to find that elsewhere as well, or has that been corroborated? What's likely?
Yeah, the evidence for the brines in liquid water on Mars seems to be getting more, I won't say solid, but more fluid as we get more and more data. It's likely that ice does play a very important role in that you have reservoirs of ice that are below the surface that are somehow not in equilibrium with their environment. And so this ice is melting, producing liquid water, then it's maybe mixing with salts in the soil to produce brines and run downhill. I didn't talk about that so much in my lecture, but yeah, this ice that's at lower latitudes is very exciting, both from that liquid water and habitability aspect, but also for future resources for humans to use. If we go and settle Mars, we can just dig down and get some ice. If you saw that Martian movie, he might not have had to spend so much time making water if he knew where the ice was. Yes?
On the section about Mars in the presentation, you mentioned that when there was investigations on the polar regions of Mars, that you were able to measure the dielectric constant of Mars at a depth of several hundred meters.
Yes. Oh, well, it uses a very low frequency radar sounding approach. And there's a certain penetration into the soil, and they measure the reflectivity basically, and from that you get the real part of the dielectric constant, and that's where this comes from.
Thank you, Dr. Paige, for your presentation. I have a conflict in my mind. You've mentioned there's a habitable zone.
Yes.
But your last comment says we're going to eventually human colonize places. What characteristics are future Homo sapiens going to have to live in these other environments?
Well, we're going to do this. We're going to do the same thing we did on Earth, where we basically used our adaptability and ingenuity to conform the environment to our needs. When you look at humans, we find them in every possible niche on Earth, from the highest polar latitudes to the searing tropics and all that sort of stuff. Humans basically figured out how to make their way gradually, basically covering the entire Earth. There's no reason why we won't be able to do that, either by re-engineering ourselves, which could be a possibility, or much more likely, simply re-engineering our environments to provide, air conditioning and heating and all the things that we sort of take for granted in our modern society, except, of course, with a high-tech twist to make it work on the planets. But it'll only work, obviously, if we're able to use energy resources and then molecular resources that exist where we are. We can't just take everything with us, because that just won't work.
It was mentioned in the introduction that you have an instrument going up on the Mars 2020 rover.
Yes.
What's this instrument going to do?
Oh, this is a ground-penetrating radar instrument. This is a method of geophysical exploration that's used on the Earth, where you can basically drag these things along and get a subsurface picture of where there are boundaries. And typically it's used to find layers or tunnels and things like that below the surface. This will be probably the first application of this technology on Mars. And Mars is a great place for radar because there isn't so much liquid water, which tends to stop the penetration of radar waves on Earth. And we expect to be able to see a lot of subsurface strata. The main purpose of the mission is to search for samples that will eventually be brought back to Earth, for analysis. And our instrument, which is built by the Norwegians, but we're participating in the development, will hopefully tell us something about what's going on below the surface and help elucidate what the stratigraphy is. And maybe discover new things too, who knows? There's one question in the back there, I think. Oh, there you go.
Where?
I'm not so sure. I mean, I haven't seen too many talks in which those two factors have been juxtaposed. As someone who looks for ice, I'm a big fan of ice, and to see so much of it go away, I did a calculation that suggests that if you look at the rate of ice loss right now, each of us individually is responsible, sort of, for the loss of roughly a volume of ice equal to roughly a large living room solid of ice. In other words, if you divide the amount of ice it's losing by the number of people, that's how much ice is getting lost every year. Now, that doesn't mean you personally are responsible for that, because this is due to this feedback effect where the accumulation of carbon dioxide, which lasts in the atmosphere for hundreds of years, has now turn the dial on the climate such that the ice is retreating at an ever faster rate. So, yeah, I think it is, looking at solar system ice, does provide an interesting perspective on it, but I haven't heard too many people, talk about it in the same hour, let alone, in the same book. Oh, there's someone in the front.
There's one right here. Can I just grab the mic?
Okay, so I'm just wondering, in terms of Mars, so you're saying that there's all this subsurface ice that exists, and so like on Earth we see, when we have permafrost, we see like structures like frost heaves and that sort of thing. And I'm wondering, is it possible, given that the just the pressure conditions and so on Mars, is it possible for things like that to form and to look for them? Or?
Yeah, for just about every sort of so-called paraglacial process that you have on Earth, there have been people who have identified images that could be interpreted as being consistent with those type of features. There's things called pingos that you sometimes see at high latitudes. We see those on Mars, and you saw the images of the cracks and stuff like that. So it's very interesting. For a lot of geology, Mars is often a better place to demonstrate it because there's no vegetation, not as much erosion. Increasingly in textbooks, you find as many pictures of Mars illustrating geology as you do on Earth, just because there aren't those awkward trees and things like that, and they get in the way. So yes.
How typical is solid or liquid H2O is Earth? Meaning, does Earth have relatively more water than the other planets, or less?
That's an interesting question. It depends. The bodies that in the outer solar system have more water proportionally, if you include their icy shells and internal oceans, than the Earth does. The amount of water the Earth has is deceptively small because, of course, most of the Earth is composed of iron and rock, and only a very, very thin shell of low-density material water has sort of floated to the surface. So while the Earth certainly has a lot more water than Venus and Mercury and the Moon, it remains to be seen, honestly, whether proportionally the Earth has more or less water than Mars does. And then certainly as you go further out in the solar system, the bodies become more water-rich than the Earth.
Thank you.
Well, thank you, Dave, and please join me in thanking Dave for this wonderful lecture.